All right, today we cover a really important topic called radians, and notice you should be working on project number 5. That's due next class, so look for a date right there next to class 18. Also next class I will assign project number 6, and then shortly after that there will be a quiz. No rest for the weary, so hold on. Okay, so let's go ahead and jump to the class notes. It says Project 6 assigned, sort of. If you do have time to start Project 6, it's available, and getting a jump on it might be a good thing. But certainly finish Project 5 before you start tackling number 6. Number 1, degrees are a fairly arbitrary way to measure angles. A more natural way is by using something called radians. Here's the definition of an angle whose measure is 1 radian. So you guys already know what 1 degree is. It's this little tiny way to measure an angle, and you know that there are 360 degrees in one complete revolution. So that's old. So now we're going to come up with a completely different way to think about measuring angles. So here's what we'll say. This is, that might be the unit circle there, but let's just call it R for some generic radius. And what I want to do is just pick any old angle. I'll pick some small angle here. I'll call it theta. So here's the question. If you take a look at the starting point and the ending point, and then you look at the arc, an arc is just a part of a circle. If you look at the arc between them, and then actually measure it. Now it's hard to measure because it's not straight, but if you took like a piece of string and you put it on there, you could then take the string off the circle and straighten it out and use a ruler to measure this. And what do you think? How does I'm going to call this guy here S, the length of that arc. The question is, how does that length S compare to the radius R? So hopefully if we trust this picture, we would say that the radius in this case is a lot bigger than the angle, than the arc, I should say. Okay, that's fine. So how about we play that game now again, but we'll use a bigger angle. So suppose that I'll use this angle right here. That's theta. Starting point, ending point. The arc is now this entire thing, which we're calling S. And again, if you envision measuring this thing, so get a piece of string and then put it there and then straighten it out and measure with a ruler, how do you think the S compares to the R now? So just looking at the picture, it sure feels like the S is a lot bigger than the R at this moment. So initially we had a tiny S compared to the R, and now we have an S that's much bigger than the R. So would you agree that there's going to be one magical angle where the S is exactly the same as the R? It's kind of like the Goldilocks and the Three Bears. Like here the S is just too small, here the S is too big, but there's one S that's just right. There's one S that's exactly the same length as the radius of the circle. So let's just ballpark where that S is. So that's still an R. And I want to draw something on the arc. I want some arc that's the same length as that red line. So here I would say that that arc is smaller. It's too small. It's getting there, but it still feels too small. Maybe something in there, maybe a tiny bit further. So how about we call it roughly there, and we'll say that this is an R, this is still S, but if we're at that magical spot, then the S and the R are exactly the same. And whatever angle happens to give us that magical spot, we are going to call 1 radian. 1 radian is the angle where the arc that we cut out on the circle is exactly the same as the radius of that circle. There's only going to be one spot that does it in standard position anyway, only one angle that does it. So that's 1 radian. And so, for example, if I were to draw another copy of that 1 radian angle, let's put it over here. So that's another R. So let's say that this theta is another 1 radian. And it gives us another arc that we cut out that's exactly the same as the radius. Then what do you think about the measure of this angle from here to here? Well, it's 1 radian plus another 1 radian. That's a 2 radian angle right there. So this thing right here is 2 radians. Okay, so you can copy the definition down from your book if you want to, but I'll just say it one more time without writing it. We define 1 radian to be the magical angle where the arc that you cut out on that circle happens to be miraculously the same exact length as the radius of that circle. Okay, number 3. Let's figure out how many radians are in a complete revolution. Okay, this is a little bit tougher, but let's keep marking up this diagram a little bit more. So we've already got 2 radians in this picture, and if I kept going, I would have like a 3rd radian. I'll use red again. So maybe 3rd radian is out there. This isn't to scale, but bear with me. We're just trying to ballpark some things here. Okay, so then we've got another R, and then this blue angle I'm saying is another 1 radian. That's theta. There's another S equals R. And so we've got, looks like about 3 radians up there. Well, I want to know exactly how many radians are in the entire circle, 1 complete revolution. Well, I guess the question is, how big is the arc, right? Because if we're going 1 revolution in terms of the angle, then we're definitely also going 1 revolution in terms of the arc of the circle. So it feels like it's important that we know the circumference of a circle. So that formula is 2 pi times the radius. Okay, so bear with me here. The circumference is 2 pi copies of the radius. So taking a look at this cluttered diagram here, I've got 1 copy of the radius there. I've got a 2nd copy of the radius. There's a 3rd copy of the radius. So apparently there's 2 pi copies of the radius here. And 2 pi is, 6 and change, like 6.3. So if you had just 1 radius, then it would be 1 radian. If you had 2 radii, then it would be 2 radians. 3 radii is 3 radians. 2 pi radii is 2 pi radians. So I guess what that means is that 360 degrees is exactly the same as 2 pi radians. Okay, hopefully you got that. It's kind of a difficult argument to follow. If you got it, great. If you didn't, it's okay. I didn't get it the first time I heard it either. But something I did get was the importance of memorizing this equation. 2 pi radians is 360, or maybe better yet, this one by dividing by 2. Pi radians is equal to 180 degrees. Stars and asterisks and all good symbols around that equation. We're going to use that a bunch, especially today. Okay, so one thing I'm really curious about now actually is how much is 1 radian in degrees? Because I've got a lot of comfort with degrees, and I think you guys do too. Part of one of the goals of this course is for you to gain comfort with radians. So I'm going to ask you to not abandon, but really favor radians for much of this semester. They are a whole lot more useful in calculus than degrees are. Okay, so then what did we say? We wanted to know how many degrees are in 1 radian. So we can just fill that in here. 1 radian is equal to, so I'll just copy it, 1 radian. It's kind of silly, but it's true. But now we're going to multiply by a fancy form of 1. We know that highlighted in yellow, pi radians is the same as 180 degrees. So what that means is that 180 degrees divided by pi radians is what magic number? Well, that's just 1. Divide both sides of that highlighted equation by pi, and you get 180 over pi is 1. So the nice thing here is that the radians cancel, and we're just left with degrees. So if we type into the calculator 180 divided by pi, then we will figure out how many degrees are in 1 radian. About 57.3. 57.3, a little less than 60 degrees. So how did we do? Did we estimate accurately there? Would you say that's about a 57-degree angle? Yeah, seems fine to me. Okay, number 5. Let's convert each of these to radians. So starting with 60 degrees, all you have to do is multiply by the magical fancy form of 1. In this case, we want to multiply by pi radians over 180 degrees because we want the degrees to cancel. So if you do that, you can get a decimal on the calculator, but let's do an exact answer. 60 and 180 reduces, and so we just get pi over 3 radians. Same kind of thing with 270 degrees. So multiply by pi over 180. And cancel or reduce the 270 and the 180, and we should get 3 pi over 2. Degrees cancels, so that's radians. Okay, 20 degrees, multiply by pi over 180. And reduce, and we get pi ninths, radians. And then finally 2 pi degrees. That's kind of funny. We're going to multiply by pi over 180. And then we get this very strange looking answer. Let's see, so we get 90 on the bottom and somehow pi squared. Don't see that very often. So pi squared over 90 radians. 6, we should be able to convert to degrees. We should also be able to convert to degrees. So here, instead of multiplying by pi over 180, which is just a fancy form of 1, we're going to multiply by 180 over pi. Cancel the pi's, reduce 180 over 4, and just get 45 degrees. So pi over 4 radians is the same as 45 degrees. Okay, next one here. Multiply by 180 over pi. How are you supposed to know whether you should do pi over 180 or 180 over pi? Well, I always find that if I'm not sure, writing the units will help me. I know that degrees goes with 180, and I know that radians goes with pi. I just got that memorized. And so if I have radians and I want to get rid of them, then I better put radians in the bottom so they cancel, which means degrees upstairs. So 180 over pi in this direction. Okay, in part B, cancel those pi's. Let's see, so we got 5/3 of 180, so is that 300? I think that's okay. Multiply here by 180 over pi. Cancel the pi's. 12 goes into 180 15 times, so that's a 15-degree angle. And then this one is going to have pi's left over because there's no pi's to cancel here, so that's okay. So we multiply by 180 over pi. And we just get 720 over pi, whatever that number is, degrees. 7. If we were to cut a complete revolution into 24 equal pieces, how many degrees would be in each piece? How many radians would be in each piece? Okay, let's see. Complete revolution, so we know in degrees, that's 360. For some reason, we're cutting it into 24 equal pieces. Not sure why, but it's easy enough to do. So 15 degrees each. That's fine. And then over here, if we want to do in radians, well, we know that a complete revolution is 2 pi radians. Still cutting it into 24 pieces. And we get pi over 12. Okay, so it seems kind of arbitrary to cut into 24, but there's a point here. So let's have a quick look at this PowerPoint slide, which is available on our Moodle site. It was created by a former colleague of mine. His name is Niels Abel. And let's go ahead and take a look at this slide. So I'm going to, so don't worry about all the stuff that's happening in the labels for right now. But if we look at these 3 lines right here, they are our 30, 45, and 60 degree angles. So if you look at the first numbers, they should look familiar, 30, 45, and 60. But this number doesn't look familiar. We haven't talked about the 15-degree angle at all. We know that 30, 45, and 60 are inside of special right triangles, but we've not mentioned 15. And we also haven't mentioned 75. But the nice thing about using 15 is that if you go up by 15s, you land on every important angle and a couple that you don't care about. So for example, 15 we don't really care about. Add another 15 gives you 30. We know something about that angle. Plus 15 is there, plus 15 is there. Plus 15, nobody cares about 75, so we'll skip it. But plus another 15, you land on 90. Okay, plus 15 is 105, don't need that one, but plus 15 more is 120. We talked about that one. And so you'll find that the middle 3 of every set of angles, together with the 4 extreme ones, the top, bottom, left, and right, are angles that we've labeled on our unit circle. Okay, so now we're going to, instead of thinking of counting by 15ths, we're going to think of counting by pi over 12s. This is going to go kind of quick. It's going to be 1 pi over 12, 2 pi over 12, 3 pi over 12. Let's see. Until we get around to 24 pi over 12. So here's the nice thing. We have just seen that, what did we see up here? We saw that, for example, 60 degrees is pi over 3, and we saw that 45 degrees is pi over 4. So let's go back to this PowerPoint, check it out again. So again, 60 degrees was pi over 3, 45 degrees is pi over 4. We didn't do 30 degrees, but it turns out to be pi over 6. And you get this collection of like really random looking fractions. Pi over 6, pi over 4, pi over 3. It's really hard to know exactly what's happening there. At least it's hard to memorize. But if you think of these as being just multiples of pi over 12, then really good things happen. So we said 1 pi over 12, 2 pi over 12, 3 pi over 12, continue all the way around. 1 pi over 12 we don't care about, but 2 pi over 12, that's 30. We care about 30. But if you reduce 2 pi over 12, you get pi over 6. Okay, the next one is 3 pi over 12. It's clear that 3 pi over 12 comes from this pattern, but if you reduce 3 pi over 12, you get pi over 4. I don't really see the pattern here, but unreduced, I see it very clearly. Let's see, 1, 2, 3, 4 pi over 12 when you reduce gives you pi over 3. Fair enough. 5 pi over 12 we don't care about. Let's jump up here. 6 pi over 12. Reduce that, you get pi over 2. So we get this collection of angles that doesn't look like there's any kind of pattern happening when you reduce. Pi over 6, pi over 4, pi over 3, pi over 2, 7, no, we're skipping that one. 2 pi over 3, 3 pi over 4. It's a really hard collection of numbers to just remember. But I can really easily remember this red collection because they're just multiples of pi over 12. And then whatever you get to the angle you care about, you reduce it. 10 pi over 12 reduces to 5 pi over 6. So I think it's a really nice pattern that's there, which maybe isn't apparent when you look at the unit circle with reduced fractions. Okay, number 8. Let's fill in a couple of the radian measures of the angles in the fill in the unit circle activity. You'll fill in the rest for homework. So you'll have to go back a few pages to find this, but we're looking for our old friend, the unit circle here. And right there where we had 30 degrees, we want to put the equivalent of 30 degrees. But in radian measure. Okay, so let's start filling in green here the radian measures. Okay, you are welcome to just memorize, and at some point you might memorize it without even intending, that 30 degrees is the same as pi over 6. But if you don't have that memorized just yet, then what you might do is say, okay, 1 pi over 12 is this angle we don't care about. 2 pi over 12 is this angle, and 2 pi over 12 reduces to pi over 6. So pi over 6 is what goes right in here. I'm going to use that blank line to be my fraction line. Okay, continuing the pattern, this next one here must be, let's see, 2 pi over 6. That must be 3 pi. Oh, something is funny. Oh, 2 pi over 12 must be 3 pi over 12, which reduces to pi over 4. So that must be this one right here. And we'll do one more together right here. So that must be 4 pi over 12. Reduce the 4 and the 12, and you get pi over 3. So I don't want you to put the 12ths as your final answers because nobody talks about them as 12ths. But I think writing them as 12ths can help you figure out what these things are, at least until you've got a bunch of them memorized. So go ahead and pause the video here and fill in the rest of these radian angles. So all of these blanks should be filled in when you're done, and then come back when you're finished. Okay, so this is a good time to make sure that your answers agree with mine here in green. So maybe pause the video, and then in a moment I'll scroll down to the bottom half of the circle. Okay, and you can pause the video again to check these. Okay, so if we're all set filling in all those radian measures, then we can come back here. So we just did number 9, and then we'll move on to page 2 of today's notes. I should say we just finished 8. So here's number 9. Here's a pared down version of our unit circle with the quadrantal angles given as exact values as well as estimates. Memorize these. Well, you can memorize if you want, or you can just know how to figure them out. That might be more powerful. So what are we doing here? Let's see, quadrantal angles in terms of radians. So we just wrote down on that unit circle that this up here is pi over 2, and this one over here is pi, and down here is 3 pi over 2, and then over here is 2 pi, also known as 0. So that's fine, but it would also be helpful to know what these guys are as decimals. So you guys all know that pi is around 3.14. If you take half of that, then you get about 1.57. if we do 3 pi over 2, so let's type this one in here, 3 pi divided by 2. We get 4.71, that's fine. And then over here, 2 pi is around 6.28. Okay, so let's see if we can use these new labels to help us with number 10. In which quadrant does an angle of 3 radians live? Okay, 3 radians, let's see. So we know that, that 1.57 gets us up to there, that's our right angle. We know that 3.14 gets us there. So 3 radians is just a hair short of that line. So in which quadrant is it in? Well, we know that the order of the quadrants is given like this, 1, 2, 3, 4. Start from the top right and go counterclockwise. Roman numerals is the standard. So in which quadrant does an angle of 3 radians live? It lives in quadrant 2. And that's really easy because we've got there the decimal numbers. Okay, next one. What are the signatures of sine 3 and cosine 3? Okay, so signature is a very fancy word which just means sign. So this question is really just asking about sine and cosine of 3. Are they positive numbers or negative numbers? So why am I using the fancy word signature instead of the shorthand version sine? It's because sine is a homonym of sine. And so it's really awkward to listen to somebody saying, what's the sine of 3? It's real easy to get that confused. So generally, I'm not super fancy in terms of what I write mathematically, but I think here it adds clarity. So we want to know the signature of sine of 3 and cosine of 3. Okay, let's see. So we've already decided that 3 is someplace in here. That's 3 radians. And we want to know about the sine and the cosine. Okay, well, we can do that. We know that we've got a point over here, and it's an x and a y. And which one comes first, sine or cosine? So it's always cosine. So there's the cosine of 3 radians and the sine of 3 radians. So the x-coordinate of this point, let's draw in purple. So the x-coordinate we can bring right down here. So this right here is the x, and then the y-coordinate is whatever we get in here. So that distance right there is the y. So let's see, the y-coordinate is definitely positive because we went up. So I guess this is a positive number here. And then the x-coordinate is negative because we went left. So those are our answers. The sine is a positive number and the cosine is a negative number. The calculator can verify for us. Okay, so if we type in sine 3 before we hit enter, in fact, before I even hit any of these 3 buttons here, I always check my mode because we go back and forth in this class. At some point, it's going to be pretty much exclusively radians, but we're going back and forth right now. So sine, cosine, tangent, those buttons, you got to make sure you're in the right mode before you hit them. So sine of 3 we said was going to be a positive number. Even more, I think it's going to be a pretty small number, right? Because we're going to be pretty close there, so maybe like 0.1 or something like that. That's great. And then cosine of 3 we said was going to be negative, and it's going to be pretty big. It's pretty close to -1, so maybe -0.8 or something like that. Oh, very close to 1. I guess what that means is that my diagram is not super accurate, and that actually 3 radians is even a bigger angle than I've marked. So it's almost exactly at the far left of that circle. Number 11, important convention. Whenever we label an angle without a degrees sign, we assume radians even if the word radian doesn't appear. Thus, sine of 3 means sine of 3 radians, not sine of 3 degrees. So pretty much we're going to be omitting that word radian just about every time from now on. But it's important to know if we mean degrees, we have to put that degrees symbol. If we mean radians, we don't have to put the word radians. It's just a default. It's just something we all agree that if you don't see a symbol there, it means radians. That's the assumption. 12. If we have a pretty firm grasp of what radian measure is, we should be able to come up with a formula that relates the measure of an angle in radians to the radius of the circle and the length of the intercepted arc. Okay, so I'm going to make up some numbers and put them on this circle for a second. Suppose that I tell you that the radius here is 5 and that the length of this arc right here is 10. Can you tell me how many radians this angle is? Well, hopefully we remember from the first thing today that if you happen to have exactly the radius along your arc, then the definition is 1 radian. That's that angle. So there's a 5 there, but there's 10 altogether, so that means there's another 5 up there. So I guess that means there's another 1 radian angle in there. So altogether, it's an angle of 2 radians. So is there something we can do with the 10 and the 5 to get the answer of 2? Sure there is. We can divide them. So I guess that's something that we can say is true in general, is that if you take the arc length, that was the 10, and you divide by the radius, that was the 5, then you get the measure of the angle in radians. Essentially, that equation right there is the definition of radian measure. Theta radians is S divided by R. Said another way, if you decided you could multiply both sides by R and get S equals theta times R, it's equivalent. Okay, number 13 says, thus we have another important formula. Yeah, these two. Note that to use this formula, theta must be measured in radians. So in 14, I'm going to try to trick you into using that formula when theta is not in radians. What length of arc is cut off by an angle of 150 degrees on a circle of radius 10 inches? Okay, so you don't need a diagram. We're just going to plug blindly into our formula. Let's see, we want the length of the arc. So that's the letter S. So how about we use the second version of this formula because it has S by itself. Okay, so theta is 150 degrees. Remember, you have to put degrees if you mean degrees. The radius is 10 inches, so we multiply by 10. And we get 1,500. 1,500 inches is the length of the arc. Now that's very strange because the radius was 10. So if you want to find the circumference of the whole thing, what do we have to do there? 2 pi r. 2 pi times 10 is 20 pi, which is about 60 inches all the way around. All the way around this circle is 60 inches. But somehow if you go not even halfway around, it's 1,500 inches. That's a problem. And you might not catch up on, I mean, if you're not really thinking about it, you might miss the fact that it's a problem. And the issue here is that we tried to use a radian formula when we had a degree angle. So we need to convert this 150 into radians. So what's our fraction? 180 over pi or pi over 180? So in this case, pi over 180 is the winner. Notice that I omit the word radian on top, but that I am required to put the degree symbol on the bottom. And so this is something that we can simplify. So what do we have here? 15, 5, 6, 56, 25 thirds. Don't quote me on that, but something like that, inches. And then we can type this in. Okay, so first let me double check the stuff that I did before. 150 times 10 divided by 180, math frac. 25 thirds, hooray. Multiply by pi. Let's see, so I'm guessing this is going to be something like, I don't know, 27? 26, good enough. Okay, so about 26.18 is what goes here. You walk for 5 miles around a lake of radius 2 miles. What angle represents your final position, and what are the coordinates of your final position? Okay, so let's go ahead and draw our lake on top of some coordinates. This happens to be a perfectly circular lake, which is super for us. It says the radius is 2 miles, so I can mark that here. That's a 2. And it says we go 5 miles altogether around. So we're going to walk around this lake. Let's just start here in our standard starting spot. And we'll say we walk for a total of 5 miles, and maybe we end around there. Okay, so the first thing we want is the angle. So we want to know what angle we have in here. Well, the good news is we have a simple little formula now. It just says take S and divide by R. 5 halves, or 2.5. We don't need to write it, but I will highlight. This is 2.5 radians. That's the angle. Really easy. Much easier to find than if I asked you for the angle in degrees. Okay, and then the coordinates. Well, let's see. We know that the coordinates over here are always of the form sine and cosine in some order. So which one goes first? Let's see. The one that goes first is cosine. So we'll put cosine of the angle, which was 2.5. and then sine of the angle, 2.5. But there's a problem here, and again, it might be easy to miss this problem. It's important to recognize this is not a unit circle. The radius of this circle is 2. And our general definition of the coordinates, x, y, isn't just cosine theta sine theta, it's r cosine theta, comma r sine of theta. So our final answer here is actually 2 cosine 25, 2 cosine 2.5, and then 2 sine of 2.5. And we can estimate these on the calculator. Okay, I think I've said this already in this video, but anytime I hit those 3 buttons, I just double check to make sure I'm in the right space. The mode here is radian, that's good. So 2 sine of 2.5, and then the same thing here for cosine. So about negative 1.6 and 1.2. Okay, and group activity is on the next page. Give it a shot before looking for the video.